Okay, so good evening, good morning, good afternoon for everybody. My name is József Koncer. I work at Wolfram Research. I'm part of the machine learning team, and currently I'm mostly working on game theory and the game theory functionality in Wolfram Language. So I want to remind you that I uploaded a notebook into the files in Pathable called Introducing Game Theory. And also I ask you to ask questions in the chat. I'm not sure that I will be able to write all these during the talk, but afterwards I really want to discuss those. Okay, and then I could start my talk. So here's a quick abstract. I skipped that because you can read that and it's also visible there. And I'm here to present live. So this will be an introductory, both an introductory to game theory, because I will assume that not everybody is expert on the field, and also talk about the introducing game theory into the Wolfram language. So first, I want to start with a quick table of contents. First, I want to talk about motivations and assumptions regarding game theory, then the basic concepts and notation. I will mention two bigger topics: the matrix games, usually called or also known as normal form games, and tree games, also known as extensive form games. Then I will show you, I hope, a lot of fun visualizations, then talk about finding equilibria in these games. I will show you that some already existing open source backends can be used. And if we have time, then I will mention a real world problem which can be used with this framework and mention the future plans. Okay, so what is game theory? A very simple definition, let's say slightly simplistic definition, is that that's the study of strategically interdependent behavior. So what is strategically interdependent? This is what I do affects your outcomes and what you do affects my outcomes. And maybe the easiest way or the quickest way to understanding is to list a few examples, like for games with simultaneous actions, rock, paper, scissors game, soccer penalty kicks, interrogation of prisoners, or there is a big other branch which is called sequential games. Usually these classical board games like tic-tac-toe, chess, Go are good examples. Then there are games containing chance moves, like poker, for example. And you can actually repeatedly play any simultaneous game, which can be then considered as a sequential game. Okay, so let's talk about the canonical example, the prisoner's dilemma, which cannot be not mentioned in any game theory introductory. So the illustration and the story is taken from the Encyclopedia Britannica. I will read this, and I want to stress some important parts of the story. So there are two prisoners, A and B, suspected of committing a robbery together, as isolated and are urged to confess. Each is concerned only with getting the shortest possible prison sentence for himself. Each must decide whether to confess without knowing his partner's decision. Both prisoners, however, knew the consequences of their decision. One, if both confess, both go to jail for 5 years. If neither confess, both go to jail only for 1 year. And 3, if one confesses while the other does not, the confessor goes goes free, and the silent one goes to jail for 20 years. So, reiterating, if they both confess, then both get a pretty big sentence. If both could remain silent, then then they would get only 1 year. And the worst outcome is for the prisoner who is remaining silent is when the other one confesses. And the best outcome for a prisoner is when he can confess while the other can remain silent. And the age-old dilemma of game theory is that if we assume that these prisoners are perfectly so-called rational, and they are only interested in their sentence, and they cannot communicate, and this happens only once, then one can deduce that the other one could be better come out from the situation if confesses, and the other one deduces the same, and by iterating infinitely many the imagined others in their head, they will come to the conclusion that they both need to confess. And so the only solution, only stable solution of this prisoner's dilemma is that both confess. Okay, then let's talk about a little more maybe known game, this rock, paper, scissors. However, this can show some interesting properties as well. So here probably you're familiar with this game. Rock beats scissor, scissor cuts paper, paper can beat rock. If both players show the same, then nobody wins and nobody loses, and otherwise one person is winning, one person is losing. Here, the blue player is the so-called row player, and the red one is the column player. And you can see the payoffs, the wins or the loses encoded with numbers, zeros, -1, and 1. Okay, and what we know, I think from experience, that in a rock, paper, scissors game, every player is doing the best if they are randomizing their strategy as perfectly as they can. And actually, this is the theory, and I think from experience, we can, so the experience is not against the theory here. What is an interesting thing, that the game is totally deterministic, the rules are totally predictable, and still still this can lead to stochastic, to probabilistic behavior of the so-called rational agents. Okay, then first I gave a very simplistic definition, but here I would go through of some assumptions for matrix games. So we will talk only about finite games, meaning that there are finite number of players. Every player can choose from a possibly different finite set of actions, also known as moves. Outcomes of the game can depend on all players choose an action. Players cannot communicate with each other. Players can randomize their strategies if it's desirable. Players are rational, meaning they are aiming to maximize their expected utility. Well, this expected utility, it's a non-trivial thing. Associating utilities to outcomes for each player can be a non-trivial modeling problem. And just to be able to connect to something for small monetary gains and losses, it can be approximately be the monetary payoffs. But in general, we just assume in this framework that we already know these payoffs, and these are known. So we already did this non-trivial modeling problem. And also all above property, including every player's actions action-dependent payoff is common knowledge, meaning that everybody knows those and every player knows that every other player knows, etc. Okay. Then let's move to another category, the so-called tree games or extensive form games. So, for example, board games, tic-tac-toe, chess, go, or poker, or basically any iterated game, any one-shot iterated game can be viewed as a tree game. And so what are the assumptions here? The gameplay can go through stages or rounds. In each round, one of the following can happen. One player can choose from finite many actions. A random choice can be made by the so-called nature player or chance player, but only from finite alternatives. Or the game can terminate and all players can receive given payoffs. Then the game must end after a finite number of rounds. I mean, we will deal only with that kind of problems. And there can be stages which are not distinguishable by some players, meaning that the subset of indistinguishable stages form a so-called information set. So we want to be able to model simultaneous games as well, or games where a player is not sure what the other player did or in what kind of state the other player is. That's why we introduce this so-called information set. And the information set, yes, so the same player needs to belong there, and the same number of actions has to be there. There must be some kind of one-to-one correspondence between the actions in the stages of a given information set. Okay, very briefly, just the mathematical structure. So a matrix game is formally a set of players, then an action set, and the utility matrix or tensor, more precisely. So every player can have an action set which is finite, but the number of actions can actually differ for every player. We call an action profile a set, a vector of actions. And then there is this utility tensor or payoff matrix. It's actually only a matrix for two players, but in general it's a tensor, or in Mathematica we would call it an array. And if we have an action profile, then this utility tensor can give us a vector, an n-long vector, where n is the number of players. Okay, and how it looks like in the Wolfram language. So if we have a two-player situation, then we would basically have a matrix where the entries are two-dimensional vectors or two-member lists. And here is encoded the payoff tensor or payoff matrix of the prisoner's dilemma, which was mentioned in the Encyclopedia Britannica. So one can straightforwardly just type this in, and then we introduce this new function, this matrix game, which can eat this utility tensor, and automatically generates this summary box with this little icon and summarizing some basic features like the number of players, the number of actions, and if you ask for it, it also tells you the maximal payoffs for each players and the minimal payoffs. Okay. Then tree games, very shortly. An extensive for game can be represented by a rooted tree. This is very nice because we can use the new tree data structure in Mathematica. The nodes are decorated, so a node can be a player node. In that case, it needs to have a player index or a player label. Then it can be a leaf node. The leaf node must contain a payoff vector, which is indicating the termination of the game, or a chance node, and the chance node don't have a player index, but it must have an action probability index. And here again, there is a restriction or a possibility. You can decide from which side you want to look this. So nodes with the same player index and the same number of children can belong to the same information set. And information sets give an extra hypergraph structure to the tree. Okay, and in the Wolfram language, so for example, it can be encoded by a set of rules. So here there is an association where we give a player index, and then it goes to there is a rule to a list which has 2 members, and every member contains again an association which has a player label and also an information set label, and then they go to another 2-member list which contain 2 leaves which contain only an association with the payoff label or a payoff key. Okay, and so okay, we can run this, and then there is a very nice function, this rules tree, which transforms this kind of expressions to a tree form. And that's how it looks like. And then there is this new function, the tree game, or the new object, which gives you automatically, again, a nice summary box about the number of players, number of nodes, and if you ask for it, then the maximal payoffs and minimal payoffs. Okay, so now we talked about the structure of the games. Now I want to mention really quickly how what is the structure of the strategies. So a strategy for a given player is only a probability distribution on the action set. So we said that the players can randomize. So strategies can be, in general, a random strategy. And if one can determine all the strategies for all players, then we can talk about strategy profile. And if we have a strategy profile, then by the weighted sum, we can calculate the expected utility for every player. This is this capital UK. And by this, we can define a central feature in this framework called the Nash Equilibrium. So we call sigma star strategy profile a Nash Equilibrium if there is no player who can deviate with his own strategy, and by that gaining higher expected utility. Okay, so this is Nash Equilibrium. The famous theorem of Nash is that every finite game has at least one Nash Equilibrium. But I will mention that there are already many refinements of this concept actually. Okay. Yes. So this is company code. So there is I have another notebook on my computer where these are defined, and here I only show you the results. So sorry for that. Okay, and I wanted to show how the actions are actually how the strategy profiles are actually represented in the Wolfram language. So jumping ahead, so there is this fine metrics game strategies, and it gives you the possible Nash Equilibria, and you can see that for rock, paper, scissors, for example, this is a list of probability vectors. So simply that's how the strategy profiles are represented in this framework. Okay, so very briefly, so a behavioral strategy for player K is represented by a collection of probability distributions on the actions, which can be chosen by the player. And for the members of the information set, the distribution has to be the same. And we call a behavioral strategy profile if we specify these probabilities for every player. And if we have a behavioral strategy profile, then we can talk about expected utilities. And then we can again talk about Nash equilibrium in sequential games as well. And there is actually another kind of equilibrium called subgame perfect equilibrium, which in simpler information sets it's very useful, and it's very much easier to calculate. Okay, so finally we are at the stage where I can show you plots. Okay, so I talked about how to define these matrix game objects, and now let's see what we can do with those. So the one thing is to ask for the matrix game plot. So here is a rock paper scissors game. This is 2 players, 3 actions, and so somehow we need to encode 2 numbers to a given action profile. So here is a 3x3 square, and in every square we need to put 2 numbers, and we do that by splitting the square into the triangles and then encoding by the color depth of the triangle the value of the payoff. So here you can see that in the diagonal place there are zeros, and the small payoffs are represented by gray colors, and then the big payoffs are represented by a brighter color associated to the player. Okay, let's see how the prisoner's dilemma looks like. So that's how the prisoner's dilemma looks like. I asked for a plot legend for this time, and here you can see that actually what this color coding actually means. So 0 is 0, years -2 is -2 years from the life of the prisoner, etc. Okay, then let's see what's happening if we have multiple players. If there are multiple players, this is the so-called dinner's dilemma. Let's imagine that there are 3 people. They are going to a restaurant, there is A menu and B menu. A menu is cheaper, and so they get one utility from eating it, but it also costs one utility to pay. B menu gives you 2 utility of enjoyment, but it costs 3 utility to pay. But in the end, they decide that they will split the bill. So it means that the best, there is a free rider logic here. If everybody eats the cheap menu and one person can eat the expensive one, then he can get the most reward or utility. Unfortunately, this logic leads to a multiplayer prisoner's dilemma, and if they reiterate this thought, then they will end up everybody will end up ordering the expensive menu, or at least this is the theory. And this is shown here. Okay, and naturally you cannot fit this 3-dimensional situation into 2 dimensions. That's why we needed to rearrange these actions and then use this dendrogram-like structure to show what's going on. Okay, I hope this is intuitive. So here we have this diner's dilemma with 4 players, with basically the same story. What I wanted to show here is that you can introduce more stripes and more players, and you can also rearrange these. So here I said that the row player should be player 1 and 2, the column player 3 and 4, and the plot underneath is the row player is player 1, and then 2, 3, 4 is the column player. And that's how you can rearrange things. Okay, just very quickly. So here is it's a coordination game where let's say Alice likes Stravinsky and Bob likes Bach. They would like to go together to concert, but one likes better Bach, one likes Stravinsky. This is again a so-called Battle of the Sexes game. Okay, because of lack of time, I would just jump a little bit. So here is how we encode sequential games where there are information sets. So we encode the players with colors. There is this dotted line representing information set, and in the leaves there are splitted squares again representing the payoffs. Here you can see a tic-tac-toe game which is partially filled, and here the game tree represents what could happen afterwards. And there can be one can win, the other one can win, or it can be actually not decided. Here I showed a situation where there are chance nodes. These empty nodes are chance nodes, and with black arrows, the probability vectors are represented. Okay. Okay, then this is how one can calculate Nash Equilibria. So basically, we have a function, find matrix game strategies. It eats games and it spits out Nash Equilibria. For small games, it's very easy and very fast. For bigger games, it can be demanding, but in general, it can give you the algebraic solution for multiplayer games. Okay, so this is a 3-player game, for example. Okay. Right. Okay, and very, very quickly, I just want to mention that there are already existing open source packages, like for example, Gambit, and we can, so it's possible to use that as a backend. If you already have that installed on your system, then it can actually use this matrix game define matrix game strategies as a backend, and you can tell what kind of method to use. There are a lot of methods, and some of them give you actually rational outputs for two-player games. It's very nice. And Gambit can handle multiplayer games as well. Okay. Another one is NashPy. This is Python-based. The problem is that it can solve only two-player games, but there is a recent activity on that. And there is just a few methods, but they are quite effective. And yeah, so here you can see, and you can use this if you have Python and then NashPy installed on your system. It's possible to use these things as a backend and use with this formulas. Okay, so maybe I skip this solving the real world problem. If anybody asks about that, then I will go back. But I just very briefly go through the future plans. So coming next is compatibility with Gambit file formats, the .efg and .nfg, because Gambit actually has a lot of example files. Then finding subgame perfect equilibria for 3 games, which will be implemented very soon. Converting 3 games to matrix games, which is useful for small games, and because in that way the full solution set can be found. Then in the foreseeable future, approximative methods, interactivity and autoplay, refined equilibria like evolutionary stable strategies, correlated equilibria, etc. And in the possible further directions are evolutionary game theory, Bayesian games, coalitional or cooperative game theory, iterated game theory, connection with other fields like reinforcement learning, control theory, machine mechanism design, etc. And actually, if you want to get more insight, there were 2 live streams with Stephen Wolfram where we actually initiated this project, and there, so the things which are mentioned in the possible future are discussed in a little depth. Okay, and thank you so much. I'd like to thank you to Roger Germundson, who was working with me on this, and also my manager, Giulio Alessandrini, and also Mads Bahrami, who actually initiated this whole project. And now I go to your questions. Okay. Okay, so okay. Well, I cannot. Oh, the lizard spoke. Yes. So if you go to the live stream, you will see. I think that's not the lizard spoke. That's the fire and water extension of rock, paper, scissors. But there are extensions, and you can, and the system can handle it. Where are the functions? Yes. So where are the functions, matrix game, tree game, and fine matrix game strategies defined? So yes, these are defined in a separate notebook now in my computer. Otherwise, those are in the so-called prototype build, and I am really hopeful that it will be well, not in 13, but 13 point something. I don't want to irresponsibly tell things, but I'm working on it. Can we get hold of these functions? Well, unfortunately, without consulting with some of my bosses, I think I can't say. Can we get hold of the round in the pub in England dilemma? Yes. What is function with 13? Well, 13 point something, I think, is reasonable. Any project to connect with neural network tools. Definitely with reinforcement learning, with neural networks. Directly, I am not sure. At some level, everything is connected with everything, but I don't see a very direct connection. Well, yes. So in reinforcement learning, usually, so there is the action space is not really feasible, and that's why you need to have some approximation. And usually they use, or this is common to use a neural net to approximate the action space. Yes. In game theory, we assume competing players do not communicate with one another except by having their actions seen. What happens if they do communicate in some way, or they both have access to some mutual information? Right. So a relaxation of this is, for example, this refinement of this correlated equilibria, where you allow the players to correlate their actions. I think the canonical example is the traffic light, and we don't need to play the chicken game in every crossroad because there are traffic lights which can actually correlate our strategies, and we can say that, okay, if it's red, then I stop. If green, then the other one stops. So there are relaxations, and yes, there are. You can relax many assumptions. We just want to first get done the textbook, the basics. Okay. Changes in the probability matrix. Well, okay, maybe I just don't get the pun, or I don't know. Can they be made available in the function repository in the near future? Well, not these, I think, but I'm about to write some actually tensor plotting functions, but not these ones. Okay. In some variants of poker, all players see the flop. In blackjack, all players see the dealer's cards. These become mutual information. Right. So in poker, you actually have a very big information sets, and by that, those information sets can be cutted down. So yes. And there is also these so-called Bayesian games, which is really much about information. Okay, and I think we are Done. Okay. Thank you very much. Thank you.